Hello and welcome to the demo video of our project Temporal and Category Based Price Similarity Network Analysis. I am Affaq Hussain along with my teammate Sufyan Akbar and Saim Tahir. Let's get into it. We will first talk about the data processing, then vector construction, how we computed cosine similarity, how we formulated graphs, what centralities and aggregation system are used, and then we will talk about the insights and interpretation from graphs and data. We use CPI data from Pakistan Bureau of Statistics. Our goal was to make network of cities based on the monthly CPI of all the seven categories for the year 2023, 24 and 25. Following was the format of data we used. These are the seven categories that we used. If we talk about the mathematical modeling and processing, the first step was the vector construction. For every city CI, we formulated a vector that consisted of 12 dimensions, where every dimension is the price of that product for that month. Then we handled the missing data. We checked for each data for the missing column, then we normalized the data. We defined a relation RY for each category such that the two cities CI and CJ belong to the relation if their cosine similarity C of CI and CJ is greater than or equal to the threshold. In other words, Ci and Cj are connected if their cosine similarity is greater than or equal to the threshold. Cosine similarity was formulated as by taking the product of price vectors divided by the magnitude of both the price vectors if you discuss the threshold effect. For smaller values of threshold, we got a large number of edges and connections, whereas for the higher value of threshold, we got smaller number of connections and edges. Next was graph creation. For the relation Ry that we defined, we created an undirected graph such that where V is the set of cities and E contain edges for every cities Ci and Cj. If Ci and Cj belong to the relation, we define a temporal relation T, which is a partial order for each graph, according to which Gy precedes Gy prime if every edge present in year is also present in Ey prime. Then we computed centralities. First was the degree centrality, which is the number of edges incident on Ci. Next is closeness centrality, that is the sum of reciprocal of the shortest path distance from the Ci to the all other nodes. Next is betweenness centralities, which tell us how often Ci lies the shortest path between two pairs of cities. In other words, how often it acts like a bridge or a connected between two cluster of prices. Next is the value centrality. It tells us how well connected a city is to other well connected cities. Weighted centrality and aggregation in which weights to each centrality and the condition that the combined sum must be equal to 1. Then we formulated a weighted sum using the formula. We also assign weights to each category with the same condition that the combined must be equal to 1. To know the overall influence of the city across all categories, we can formulate that by using the formula where alpha is the weight of for the specific category and SIC is the weighted sum that we formulated earlier. By using different values of weight for centralities and categories, we can get different results. For example, by choosing a higher value for the weights of food tech category, we will emphasize on food similarity, while by choosing the higher value for the weight of degree centrality, we will get cities that are more connected. Then there is a weighting strategy. The first one is the equal weighting strategy, in which we assign the equal weights to all centrality at 0.25. Next is correlation weighting system, in which we computed pair-wise correlation among all centralities, and if two pairs were almost always similar, that one of them will get lower weight. Next is category importance weighting, in which we give different values to the weights of categories. Next is entropy based weighting. Entropy tells about diversity. If a C varies a lot from the city, that gets a higher weight since it carries more information about the differences. Next was interactive weighting system, in which a user can use a slider to change the values of weight and analyze the light difference and changes.
This first Python code categorizes the data. It takes the data as input and using a dictionary type system, it assigns to every product a category. For example, to electricity and gas, it assigns a category of utilities and transport. Next step of data processing is data verification. This file reads the data and checks the presence of all the 6 columns. The next step of data processing is loading the data, cleaning it and normalizing it. This Python code does that. This code right here handles the missing data. Here we do the verification of categories. Then we also filter the defective data out of our code. Then we assign these data into tables and normalize them. Here we are using min-max scalar for normalization. This next Python code computes cosine similarity for each pair of cities for each category, then normalizes the results. It first loads the normalized data from the processing step, then computes the cosine similarity. It uses a built-in function of Python for computing cosine similarity, and then it normalizes the results and saves the matrix in CSV file. This Python code creates the graph files for data. It creates .gexf and pickle files that will be later used for creation of Hesse diagrams and temporal networks. It loads the similarity matrices that we had created in cosine similarity code. Then, based on different thresholds for every category and every year, it creates the graph files. These graph files are saved as pickle files. Then we also analyze these graph files for different thresholds and save the data in CSV files. This Python code computes centralities. There are 4 kinds of centralities: degree centrality, closeness centrality, betweenness centrality, and eigenvalue centralities. Following are the formulas for computing these centralities. This code first loads the files, the graph files that we had created in the previous code. Then, for each graph file, it will compute first degree centrality, then the closeness centrality, then the betweenness centrality, and at last the eigenvalue centrality. After that, it will store result in the CSV files. It will also normalize the results of centralities. Here also we are using min-max scalar for normalization. This Python code implements 5 different weighting systems. Here is given the formula for computing weighted sum. First we load the data of centrality that we had created in the previous file. Then first we implement the equal weighting scheme. Next we implement the correlation based weighting scheme. The formula that we are using is same as given in the PDF file. Next we implement category importance weighting scheme. It uses the categories as defined right here. These are the category weights that we have defined. And here is the function for implementing category importance weighting. Then there is entropy based weighting scheme. It uses the same formula as it was defined in the PDF. Here we have temporarily hard-coded the interactive weighting system. Later we will implement it using sliders. Till now we have done data processing, we have computed cosine similarities, constructed the graph files, we have computed centralities and implemented weighting systems. Now is the time to create Hesse diagrams and temporal networks. Before that, we will define a temporal relation and verify that it is a partial order. We will first load the graph files and ensure that the output file exists. We will start with generating the temporal networks for all centralities. Here, for each year, for each category, we will create a temporal network. We will also generate this temporal network in grid so that we can compare it easily. Here we will verify that the temporal relation we defined is a partial order. These are helping functions. This function verifies reflexivity. This function verifies anti-symmetry. And this function right here verifies transitivity. At last, we will generate Hesse diagrams. For each category, we will generate a Hesse diagram and then we will save the results. Now is the time to implement the interactive weighting system using interacting visualization dashboard. We will create sliders for user to tweak the values. We'll create a drop-down for category selection and we'll show a network of top 10 cities. This network will have node size based on the centrality, and we will also give an option for exporting the current view as PNG. We will load the data from the CSV file. Here we are designing the dashboard. Here, based on the current values of sliders, we are creating a network graph. Lastly, we will implement a comprehensive comparative visualization. In this, we will create heat maps for similarity matrices. We will create side-by-side network comparison graph and bar charts for comparing top 5 cities. We will also generate line plots to study the evolution of data across years. Lastly, we'll create clustered heat maps. So we will start off by loading the data from CSV files. First of all, we'll create heat maps for similarity matrices. Here, for every year, for every category, we will generate a heat map. Then we will generate side-by-side network comparison graphs. Similarly, here, for every year, for every category, we will generate a network comparison graph. Here we are using equal weighting system and category based weighting system. We have chosen these two for now. Now we will create a bar chart for comparing top 5 cities. Here we are creating line plots for studying the evolution of data across years. And lastly, we will create clustered heat maps for every category. At the end, we will store the data and statistics. So here, this master script helps us run all the other scripts in the right sequence at once.
So this was the raw initial data we assigned to every product, a category. Next, we normalized the data. This is the result of computing cosine similarities among every pair of cities. We computed 4 different kinds of centralities for every city, for every category. Here are the results of our centralities, and here are the normalized form of these results. Implemented 5 different weighting schemes. Here are the overall results for every city. And based on these results, we calculated the top 5 cities. So this right here is the interactive dashboard. Here on my left, we can see the sliders of which user can change the values. Here we see the current values of weights. Here we see the current score of each city. On the top right, we have the temporal network of cities. Here we have list of top 3 cities. And here we can toggle the category we are looking at. If I change the value of sliders, we see the change in scores of cities and in temporal network. On the right, we have a hazard diagram for a category for 0.8 threshold, whereas on left we have the same categories hazard diagram for 0.6 threshold. This is a temporal network for 0.6 threshold, a temporal network for 0.7 threshold, and next is a temporal network for 0.8 threshold, whereas this is a temporal network for 0.99 threshold. We can clearly see that the number of edges keep on decreasing if we increase the threshold. The result of verification of partial order is displayed on the console. When I run the program, here is the result. It says reflexivity holds, antisymmetry holds, and transitivity folds. This is also a heat map. We have names of series in the bottom and on the left, and cell that corresponds to any of the two tells the quotient similarities between two. The brighter value has larger quotient similarity, whereas the darker blue one has a smaller one.
This is a heat map of a category utility and transport for the year 2023. This is the heat map for the same category for 2024, and this is the heat map for the same category for 2025. With these we can see that there is almost very little change across years. This shows consistency in the price changes across the cities of Pakistan. This is a network comparison graph for utility and transport for equal weighting scheme and category importance weighting scheme. Here we can see that by the change of weighting scheme, the ranking of cities change. If we compare top 5 cities in different weighting schemes, for 0. 0.6 thresholds we have Sargodha, Karachi and Islamabad as high ranking cities. For 0. 0.7 threshold we have Quetta, Islamabad and Sargodha as high ranking cities. Whereas for 0. 0.8 threshold we have Karachi, Faisalabad, Sargodha as the high ranking cities. And lastly, in the 0.99 threshold we have Islamabad, Rawalpindi as the high ranking cities. If we study the evolution of changes through line plots, here is a graph of centrality evolution across years for top 5 cities. If we study the degree centrality, we can see that from 2023 to 2024, Sargodha has had a very high jump, whereas Rawalpindi has had been a very stable city. Clustered heat maps help us identify the best pairs of cities. Here on our right we have the 7 categories, and in the bottom we have made pairs of cities. We can see that the best output pair is Islamabad and Rawalpindi. This result is for the threshold 0. 0.6. This is the clustered heat map for 0. 0.7 threshold, and here again we can see that Islamabad and Rawalpindi have proved to be the best for all categories. This shows consistency and strength in the economy of twin cities. Lastly, if we analyze the top 10 cities for 0. 0.6 threshold, they are Islamabad, Sargodha, Rawalpindi, Quetta, Karachi, etc. For 0. 0.7 threshold, we have Sargodha, Islamabad, Multan, Quetta, Karachi on the top. Whereas for 0. 0.8 threshold, we have Karachi, Multan, Gujranwala, Quetta, Islamabad, Sargodha on the top. And lastly, for 0.99 threshold, we have Islamabad, Rawalpindi, Gujranwala, Sialkot, Multan on the top.
In conclusion, we constructed a temporal, multi category network of cities based on CPI similarity. By implementing and comparing multiple weighting schemes, we provided a nuanced view of urban economic influence. This project highlights the power of network analysis in revealing the complex structure of regional economic integration.